Welcome, I'm Emily Crew.
And I'm Sarthak.
Over the past few weeks, we've worked on a summer research project at UConn Stamford under the guidance of Professor Bradford, whom we would like to thank for all his help.
Today, in order to present the culmination of our work, Emily and I are going to discuss the significance of labeled path problems and an interesting application related to network security.
So, suppose I want to send you an email across the internet without the intermediary nodes knowing that the final destination is you. How could I do that?
Well, you could use something we call an onion router.
Before we discuss onion routing, we'll begin by introducing labeled path problems.
These are graph problems where we want to find validly labeled exact paths from a source node to any end node.
Take this graph for example. We use the context-free parentheses language, called a Dyke language, to label the graph edges. We represented +1 edges with open parentheses and -1 edges with closed parentheses.
An exact path would be a case where the open and closed parentheses cancel out, like this. For example, one exact path in this graph would be from node 1,1 to node 2,2 because the open and closed parentheses balance out.
This idea of exact label paths can be applied to network security, specifically onion routing.
An onion router looks something like this. It is a series of encryptions and decryptions that surrounds a message in layers, similar to the structure of an onion.
We are interested in routing data packets through this graph. Each node either encrypts packets arriving, represented by open parentheses, or decrypts packets leaving, represented by closed parentheses.
DES stands for Data Encryption Standard, AES is Advanced Encryption Standard, and TF is two-fish. These are all encryption functions, and in this case they're each represented by a different style of parentheses.
This brings up commutativity. The parentheses and decryptions have to be in the right order. For example, this graph would not work as an onion router because the parentheses, and therefore the encryption and decryption functions, are not matched correctly.
However, a properly arranged onion router will have parentheses that solve to an exact path, just like we discussed before with labeled path problems.
When this system is represented with the parentheses language, like in this example, you can see how enclosed the message M is by encryptions and decryptions, and how it is gradually revealed as these functions are matched at the different parentheses levels.
The system is very beneficial for network security. The core principle of onion routing, referred to as the Onion Routing Project, or TOR project, emerged in the 1990s by employees working in the United States Naval Research Laboratory, who wanted a way to protect U.S. intelligence communications that took place online, and this was also further developed by DARPA.
Tor is perhaps the largest anonymous encryption communication service. The benefit of onion routing is that each node only knows the identification of the nodes directly before and after, and nothing else. Furthermore, no node interacts with both the origin and exit.
The nodes are unaware of their place within the process, and therefore don't know if the surrounding nodes are a source, destination, or just another intermediary node like themselves. No node in the process knows everything about the route as a whole.
This allows the identification of the sender and the receiver of an email, for example, to remain anonymous, because sometimes just knowing who is talking to whom exposes valuable information.
This is very important because some other encryption techniques only hide the message itself, but not the actual sources that are involved.
To summarize, we have discussed how onion routing works, and how they can be depicted by a graph with edges labeled by a parentheses language.
This relates to network security in that we could send a message while hiding both the source and destination.
Thank you for watching.